I thought I'd just give you a bit of an unconventional talk. Since you're all geologists and not brokers, we can go into the nitty-gritty detail, which is a pleasant, very pleasant sort of change for me, to talk to people who actually understand what you're saying, mostly. So I'm going to swap between just showing a few things on the PowerPoint and real time in some 3D software, which we use to model Kalkaroo. So if it seems to you that I don't know what I'm doing or I'm totally confused, you're probably right. But hopefully I can keep talking. So Kalkaroo's up in the northeast, about 50 kilometres north of the main Broken Hill Highway. It's out in no man's land here, the flat country. There's no outcrop, up to 70 metres of tertiary clays related to the Lake Frome Basin. It lies within the Curnamona province, which includes Broken Hill, about 17-20 million years old. Mineralisation here is probably around a bit nearer 1600, and it's a reasonably sized deposit, and that's the published JORC Resources. And it also has a supergene gold cap, which is devoid of copper, sitting on top. So I'll start backwards here. I'll go into the detail first and then expand out into the regional geology. So you might like to just keep in mind what the ore body looks like, because it'll help you as I go through, build up the picture. Basically, I'm going to sort of go through the anatomy of the deposit and how we've arrived at the conclusions we have. But it's a very long deposit. It's about nearly 3 kilometres long, and it's like a big dipping coal seam, is the nearest you can describe it. It's 50-80 metres thick, dipping down about 45 degrees to the north. Superimposed on the primary sulphide, you have supergene weathering, so you have a very well developed gold cap sitting on top of the main copper gold ore body. So that's why we've separated the resource into a gold cap and then the main copper gold ore body. Discovery history. If you're like me, it's always nice to know how deposits were discovered and how it came about, because it can help you find the next one. So this is a classic sort of deposit discovery, I guess. 3 other companies discovered it before us, so it's not a new discovery. We can't claim it as a virgin discovery by any means. Placer were the first on the scene in 1993, and they were drilling an area mag anomaly, presumably after an Olympic Dam style target, and they put some drill holes right through the middle of the ore body, and knew that they'd hit something. There was no way that they missed it, and they estimated a resource of 5 to 10 million tonnes, too small for them. They joint ventured it to Newcrest in 1997-99, who were looking for large open pittable gold deposits. So they drilled, used their particular technique, which was shallow air core drilling to bit refusal, and they did drill a few diamond holes. And they got plenty of minor hits, but they didn't really target the known resource that Placer had got to try and expand it. Then they withdrew for no interest. MIM come on the scene, joint ventured with Placer up to 2003, and they used MIMDAS, deep looking IP. And they actually followed up with a number of diamond holes, but they didn't concentrate on the resource again. So in the depths of despair in about 2004, I think, when David Lowell come here and said, take heart, people, because I've seen all this 5 times in my career, the copper price will recover. I don't know whether any of you were at that talk, but it was quite it was amazing talk. And anyway, that was about when we acquired the interest from Placer and MIM. And majors were going broke and divesting their interests, so that was good for us. And the thing that was of most interest to us, we inherited a huge database of drilling from 3 different companies who had never actually tried to integrate the data. So the first thing we did, being a little company with very limited resources, we did what was easiest and simplest, and we This is where I'll go into Vulcan now. We just took the data that was there, put it all in one database and tried to make sense of it. So this was the slate that we started with. You can see the scale here, 5 kilometre grids. Quite a lot of drilling done by three different companies. So all of this regional drilling here was all Newcrest drilling, air core drilling to bit refusal. These holes here with the colour, basically anything yellow is at 0.25% copper. So anything warm colour is of interest to us. These are the placer holes. Placer did some air core drilling here. They also did a few diamond holes, so that's an original placer diamond hole, but Newcrest also did some holes here. Let's see what that one is. Anyway, I'm pretty sure, yeah, that's a Newcrest hole, KND. So placer, this is where they defined their 5 to 10 million tonne resource, and they drilled a few diamond holes, a couple of different directions. MIM drilled a few holes. This is a very deep hole out here, which we're eternally grateful for because it got about 300 odd metres of low-grade copper in it. That was drilled on a MIMDAS anomaly, and various other holes. So that was what we started with, and then of course a lot of regional exploration out in the boondocks, targeting structures and magnetic features. But you'll see there's not too many anomalies in the bottoms of those holes, but there are a few. Anyway, so when we got the data and looked at it, we were most interested in this area here, and Bob Johnson did quite a clever thing, I think, in that he looked at the drill holes here, and there was quite a number of intersections, and he took the drill holes where there'd been a complete intersection through the mineralisation. So where it went into mineralisation and went out. There are a number of placer holes here which just went into the mineralisation, but not so many that actually went through it. In fact, out of 500 holes that were drilled here, there were only 6 which actually went right through the complete section mineralisation. So you can see that here. You can see these holes here, for example, they're air core holes. They stopped in mineralisation, all of them. But a hole like this went through the mineralisation. This one, a couple of others. So as I said, he did what I thought was quite a clever thing. He actually tried to fit a surface to it, and it was just basically a trend surface, and without trying to influence the data or do anything at all. And when you took the intersections through the 6 key holes, you found that it formed this parabola shape. And you'll see a lot of the drilling. I don't think the previous geologists were necessarily aware of that. That the mineralisation actually was forming this shape. But anyway, the key holes were about 6 intercepts through. You can see them coming through here. This hole, this one, about 6, and that's what defined that shape. So anyway, we thought that was quite a good conclusion, and so then we proceeded to decide how we would explore it. And the thing that we noticed was that this was actually following the stratigraphy, which in retrospect is not an earth-shattering revelation, but at the time you can see no one had really targeted the stratigraphy. So we come along and with our ideas, and we did some drilling ourselves, RC holes actually, and I'll show you them. So the holes we drilled are these, which I've just differentiated because they've got discs instead of just the colour down the length of the hole, so you can see them more easily. So you'll see what we did. We followed our convictions of the curving stratigraphy, and we drilled about 87 holes, I think, and every one of them, except the first one I cited, which is this one here, hit mineralisation. I think that's hole 1, and it was too far up sequence. But every other hole, you can see our holes here. We started drilling here where the best placer intersections were, where we had most information. But we didn't follow the placer line. We went at right angles to what we thought was a strike, based on this curved surface. And so we went around the big boomerang and kept drilling at right angles to strike. And you can see all these holes had good copper intersections. This is coloured by copper, not gold. There's also gold. Remembering this is sort of this is the footwall contact. This is the base of mineralisation. So hence all the mineralisation is above this. And so it goes round. It wasn't a fluke, because when you look, the orientation of the holes on this side is almost at 90 degrees to the orientation of the holes on this side. So we were definitely following a big boomerang. And as I said, that was the when we realised it's quite a bit bigger resource than what placer found. And of course, subsequently, if one looks at the ore body shape from the block model, that's where the ore body sits. So our drilling actually followed the ore body pretty well, or at least defined the ore body pretty well. It's grown a bit and got a bit more complicated, but basically those first 80 odd holes followed around this big boomerang, and were all in mineralisation, helped define the ore body. In fact, some of them, those holes have been used in the resource. Anyway, it's very interesting. It's a salutary lesson. The reason I make this point is not any other reason than just to give you the history and to show you, if you didn't already know, how easy it is to actually drill holes right next to let's say it's about 150 million tonne ore body all up, and not actually get any indication or actually miss it. It's so easy. And I'm not saying this to appear clever or anything like that. It's always great to, with the benefit of hindsight, to see why certain holes didn't. And you can see these holes here, for example. You're so close to the ore body, but they were drilled parallel with the dip of it. So they had no hope of intersecting the ore body. These holes out here, well, they were way up in the footwall, which was unmineralised because the ore body crops here. So they had no hope. There were certain other holes, which come pretty close, but which are also semi-parallel with the ore body, that didn't have success. There were some deeper diamond holes out here, which should have hit the ore body, but they were too far out, so they didn't actually get deep enough. And then there are some other holes out here which are very, very interesting for the upside. But when you consider out of the 500 odd holes in this region, probably only about 20 were good intersections, and this ore body actually snakes around so many barren holes. It's quite a salutary lesson. And of course, if you didn't pick up from what I said initially, there's no outcrop here. We're under 60, 70 metres of cover, so you've got no hope of seeing anything on the surface. Anyway, so when you look at the aeromag, some of the best aeromag we've got is still some of the MIM imaging. I don't know whether you did that, Jim, did you? I'm sort of blaming you, but it's a brilliant imaging of the MIM that MIM did. We've flown more detailed aeromagnetics and haven't actually been able to improve on their imaging to any great degree, anyway. Anyway, so when you look at this mag image, thanks to MIM, you can see that there's a major magnetic high here, and that the ore body is following around actually what's the north plunging nose of a dome. So when you look at it in its bigger context, here's the dome. This is the prospective sequence running around here. and we're just scratching around on the north plunging nose of it. And through here, of course, is a major fault. So if one has a look at that, you can sort of get an idea what's going on. There's quite a substantial fault run through here, chops both ends of the ore body, and there's actually mineralisation along it. But this part of the dome here is intact, and it's just dipping 45 degrees to the north. Comes around here and gets a bit messed up, and then comes back here. But that's what I'll show you next. I'll go into the anatomy of the deposit, how we put it together. But this is basically just the discovery history, and with the benefit of quite a bit of hindsight. So I'll proceed to remove some of these things and go back to our drilling now. So I'll remove the all these historic drill holes. And I'll load up our drill holes. Well, this is actually mostly our drilling, but it also includes quite a lot of, we have used some placer holes and some Newcrest holes where they were useful for our purpose. I'll load it up by copper. I'll just get rid of this here. Then I'll describe our results. So these holes here are a mixture of our drilling and all the other drilling actually. So it's very hard to pick out what's ours. But basically, all these holes that follow around the arc here and out here on the western limb are all our holes. Actually, I will just jump the gun here. I'll just take them off for a minute. So I'll show you how we actually put together the architecture of the Kalkaroo ore body. Just bear with me a minute. I'll find some things here. Okay, so the Kalkaroo has a very well defined footwall, and this triangulation surface is actually based on the results of about 400 drill holes, very careful logging, where we're actually looking for particular horizons, and it has a very well defined hanging wall. So there you have the basic architecture of what's controlling the Kalkaroo ore body. Have a well-defined footwall, well-defined hanging wall, and about 100-120 metres gap in between. At this end of the ore body, we have a fold structure, which is a result of disturbance by the fault. So we have a major fault zone come through here, and then we have a shear which comes through here, which actually just doesn't add any mineralisation, but it just slices the ore body. So if you look, this the red is the quartz vein fault zone. It's up to 80 metres wide. It's a major Breccia fault zone. It's actually mineralised, and it cuts through the nose of the dome, and actually truncates the ore body or interferes with the prospective sequence at each end. So I'll be talking a lot about the footwall, the hanging wall, and the prospective sequence. So at this juncture, I'll just duck across to the PowerPoint, and I'll just show you some pictures, and then it will make the Vulcan a bit more understandable. Sorry about the quality of this, but as I said, we have a well-defined hanging wall. We have what we call a mine sequence or prospective sequence and a footwall. Within the prospective sequence there are quite a number of horizons. It's basically an evaporitic sequence with a lot of carbonates, and it's a redox boundary. When you go from the footwall through to the Hangingwall, you're going across a major redox boundary. The footwall is quite oxidised. You go transition through the prospective sequence, and then you go into very reduced peelites, and I'll show you some of these rocks. Again, sorry for the quality. This is Hangingwall. This is albitised peelites. They're very, very finely laminated. They would have been quite carbonaceous, fine grain shales. This is typical of the footwall. You'll see it's more sammitic. It has this very characteristic flazer bedding in it, micro cross bedding, flazer bedding, a lot of slump structures, definitely coarser grain. You'll see the difference in the colour. These rocks are generally, although these are albitised, so they're bleached, they are far more prolific, carbonaceous. These rocks here are far more sammitic. Then in between the footwall and the Hangingwall, we have this what we call the prospective sequence, which, as I said, is strongly evaporitic. And we have these unusual things which Graham Till and others call ellipsoids. And very characteristic of the prospective sequence are these ellipsoids, which are probably diagenetic, either diagenesis of gypsum or carbonate. There's certainly plenty of carbonate beds. This is just a detail of one of the ellipsoids showing some of the textures. There's beautiful, this is not deformation. These rocks are virtually undeformed. They hardly have a schistosity in them. So what you see here are actually original sedimentary features. So you get this beautiful slumping, load casting around the ellipsoids. So it tells you the ellipsoids are actually growing in situ in the sediments prior to them being compacted. Not only that, you see in this ellipsoid, you'll see the sulphides here are actually following the original bedding. So the original bedding went straight through here, and this ellipsoid grew in the bedding and actually replaced the bedding. And then it formed like a kernel, and then you got the compaction of the soft sediments around it. Now these things, incidentally, are commonly found in the Zambian copper belt. Typical, there's two types of mineralisation. We have this fine replacement mineralisation where we have chalcopyrite replacing fine carbonate and carbonaceous laminae. So this is mostly chalcopyrite here, this material, and it's micro replacement. Sulphide textures. Here we have chalcopyrite intergrown with molybdenite. There's a lot of molybdenum in this ore body. Evidence for sulphide replacement. We also, the other type of mineralisation we find here is vein style, which I'll show you some examples of. But the thing that's very revealing is that in this vein style mineralisation, you see how the sulphide, this is actually pyrite in this case, not chalcopyrite, but chalcopyrite does the same thing. You'll see coming away from the, feathering away from the veins, you have sulphide replacement of a particular laminae, and then it just dies out. You can see the same thing here. And this is another example. Here's a little vein fracture, and then the sulphides come out from that, and they just peter out as you go away from that. So it's almost certain the mineralisation was introduced along fractures and veins, and then just spread out and replaced very fine laminae. You can see here. As I said, we get common fracture vein style mineralisation as well. Some beautiful examples of hydrofractured breccia with a matrix filled with sulphides. This chalcopyrite just actually occupying fractures in the rock here. You can see the brittle fracture, and the chalcopyrite's just infilling it. It's come up along a quartz carbonate vein here. Again, more examples, hydrofractured breccia with sulphides in it. It's very common. So the vein style versus the straight replacement laminae are roughly 50-50. Then we find in the footwall, and associated with that major fault I showed you, good breccias, beautiful breccias, magnetite breccias with chalcopyrite all through them, running good grades of gold. We'd love to find a big body of this. Other more typical sort of fault breccias where there's been a quartz vein that's just been absolutely torn apart by subsequent movement, also mineralised. Biotite alteration. This is a classic. The rocks are highly albitised, so they look like cherts, but in fact they're very finely laminated peelites. You can see the very fine bedding here, just been totally replaced by albite, giving them this cherty appearance. Subsequently, you've had biotite following along these veins, biotite alteration, due to potassium metasomatic front, and you can see the front here. The black is mostly biotite and magnetite, so pretty high temperature. Okay, so we'll go back to the Vulcan story again. So now you know what the Footwall and the Hangingwall Rocks look like, and when I talk about the prospective sequence, what it looks like. So with this in mind, I can actually load up all our drill holes now to show the evidence that we we base all our interpretations on. We've taken a lot of trouble to log the holes properly and try and develop a very consistent picture. So there's all the holes, and you'll see that within the prospective sequence here, between the blue footwall and the hanging wall, is where all the colour is, where the mineralisation is. There's also mineralisation along this fault zone here, but as you can see, our drilling's pretty sparse, so we certainly haven't done that justice. When we come down to this end here at West Kalkaroo, you can see there's a lot of mineralisation. In fact, our best grades are within the prospective sequence where it's cut by the vertical fault zone. That's where we get our best grades of mineralisation. It's also where we get the best supergene ore. So that's the evidence. We've logged all these holes, the RC holes, the diamond holes, to actually get piercement points on all of these features we mapped here. Now the other feature to note is that this shear here doesn't really do much. There's no mineralisation along it. It looks like a very late feature, and it even seems to displace this fault zone here slightly. And this fault zone is actually drug into it. There's late fluorite, a lot of fluorite along it, and it could even be a Delamerian age structure, or certainly had some Delamerian age mineralisation coming up it or remobilising. So that's what the ore body looks like drilled out. Now, so what I'll do is put up the triangulations of the ore. So this is a triangulation actually from the block model. So it's the actual ore as defined in our block model. There's and the yellow is the gold, and the purple is the copper gold. So you can see again that well, you can't see the drill holes now, of course, but all the intersections of the drill holes are actually what's defining the ore here. So you don't see much colour outside. The thing that's interesting is that there are some deeper holes which are drilled by other companies, Newcrest, MIM, which show that down dip, the mineralisation is still going down dip. So in fact the Kalkaroo ore body as defined here is defined entirely by our drilling. Actually, it's not defined by the geology running out, and you can see that very well here. You see we have a drill hole here, and it's been projected as far as we dare, and certainly mineralisation continues on, but we can't push the resource any further down dip because we just don't have the drilling information. Same here, although we know the mineralisation continues on. So it's an interesting ore body because in every direction, down dip, along strike, this end we end in ore on the eastern end, and similarly on the western end up here, we end up in ore. So it's actually open in all directions. It's literally open, and it's only our lack of drilling that's defining the limits of the ore body as presently defined. So getting down to this West Kalkaroo end, what I'll do is just take a section or two. We'll just do some sections through the ore body to show you what it looks like. take a section there. Let's see, put up an overview window so you know where we are. This is just simply to show you where we're sectioning. This is the section line, this blue line. This is the boundaries on each side, but this is actually a section line. So if you watch that, you'll see what's going on. Just watch that blue line, and as we slide through it. So we can just slide through. We're going towards the west now. Now the purple is the actual copper gold ore body, and the yellow is the gold cap sitting on top. And remember too also that this is where our main prospective sequence is meant to be, but because we have faulting here, we have mineralisation coming well up into the hanging wall. But you'll see the fault start to come in. So now you can see the fault here, the red coming in here. As we go further east, you see the fault start to come in, and you'll see the mineralisation rises up into the hanging wall above that fault. But it still continues in the prospective sequence. And again, it's limited by our drilling. We don't have drilling here, and we don't have drilling here. You'll note very carefully where our drill holes are. They're basically just defining a very narrow corridor around here. What happens down dip and up here, we just really don't know. But we have very good mineralisation here at West Kalkaroo, very good grades, adjacent to this vein within the prospective sequence. So it goes on. As I said, anything yellow this is coloured by copper, is good. Now what's happening here is you can see that shear coming in. So if we just take a view here, this is the shear. We're moving up towards here, and we can see this shear starting to come in. You'll see it diving in here. So it cuts through, and once we go through it, the ore body starts to go around the big boomerang, and but what you see is that this fault here, which is coming through here, which come through West Kalkaroo, is actually getting separated now from the ore. So you'll see that the fault and the ore zone are starting to, or the main dipping ore zone, are starting to diverge until the fault is actually some distance away, and the mineralisation between the fault zone and the strata bound replacement mineralisation is starting to get separated. As I said, there's mineralisation along this fault, quite good gold mineralisation, long intercepts of low grade gold, but we haven't done it justice with the drilling because it's sort of outside our pit design. I can actually show you our this is our open pit design based on the block model here. So we do actually capture a little bit of it, but not a lot. So we haven't spent a lot of time drilling it. Obviously, if we could find a lot of ore in here, then we could have a much bigger pit. The economics would be better. As it is, the stripping ratio of the ore body is about 3.2 to 1, so it's not too bad. That's mainly because of the width here. We're looking at sort of 100 metres width here. So we just continue around the ore body. You can see it's just dipping away to the north now. So we're coming around. We're right in the nose of the structure here. So continue on. Now the problem here is we're getting a bit oblique to the section. So I'll just pull this back. So we actually need to need to take another section around here which is more at right angles to the strike. So again, this is where our section line is here. And you'll see what's happening as we go further east. You'll see this fault starting to come back to hit the eastern end of the ore body. It's coming back in, and about this point they're starting to collide, and again we get good mineralisation. But you'll see what our open pit's done. We've got our open pit's captured it here, but because we don't have adequate drilling to define the resource properly here, we've sort of closed the pit off. But there's probably still a lot of mineralisation continuing on out towards the eastern end here. And basically beyond this point there is no drilling, so we have no idea what happens. But we do know that the prospective sequence actually from the magnetic curves around here, but the structure still continues on. So we've still got quite a lot of drilling to do out here. So that's the basic architecture of the Kalkaroo ore body. And there's one other important geological aspect which one needs to know about it to understand it fully, and that's the effect of weathering and supergene enrichment. The ore body shows a brilliant supergene enrichment effects. So we have a very good development of secondary copper and gold above the zone of weathering, above the water table, and we go down to chalcocite and primary sulphide. So here this is native copper just sitting in saprolite and the primary sulphides. So on the top we have native copper mineralisation, very high grades. We've got about 20 metres thickness of this type of material. It's all secondary copper, which is just redeposited in fractures and beautiful little dendrites. This is just more examples, and it can be treated by screening. There's gold associated with it, which can be recovered. Below the native copper zone we go into chalcocite. It's a secondary sulphide mineralisation. That can be very rich. So this is just basically chalcocite replacing chalcopyrite in veins and fractures. Sometimes the chalcocite replaces pyrite, but generally the chalcocite zones are quite high grade. And then of course we go down the primary sulphides, where this is very typical of the chalcopyrite. So just to give you an idea, 13% of the tonnes are saprolite gold. Well, I guess metal's more important. 13% of the copper is as native copper, 26% is in the chalcocite, and 60% is in the chalcopyrite, the primary sulphide. That's out of the total resource we've defined now. So if I go back to Vulcan again, I'll show you how that plays out. I have to get rid of a few things here to avoid complete confusion. Gets a bit tricky from here on, so you'll need your geological interpretation skills. So remember, this is Footwall, Hangingwall, Prospective Sequence, copper gold ore body, gold cap. So we're going to add a few things to it. First of all, the base of the saprolite gold here is this layer here. Again, all of these, every drill hole we've logged these things. So base of native copper, there, not so exciting that at the moment, but it does get exciting. And base of chalcocite, and that's basically all we need to know at the moment. Oh, I guess base of the Namba formation. The Namba is the tertiary clay. So this is the base of the tertiary clay. This is all tertiary clay. We have a saprolite, deep saprolite weathering with gold enrichment here. Anyway, as we, with those layers now loaded, if we go and do our exercise again and just drag through it, you'll see very interesting things happen when we hit the main vein zone, which comes through here, and here's the vein here, we find that because the rocks are more sulfidic, they've weathered more because of the release of sulfuric acid. Also the fracturing, the weathering drops down. So you'll see here the base of chalcocite drops down dramatically. The same with the native copper. This is the native copper. It follows the fracture down. The gold, well, it tends to be fairly well behaved, but certainly the native copper, we can drill a hole here. For example, we'll go through chalcopyrite, then we'll go into, chalcocite, native copper, chalcocite into chalcopyrite. So the distribution of the copper minerals is quite complex. So again, this is the fault zone here. I hope you can see it. This is a chalcocite, base of chalcocite, base of native copper, base of gold. And we see that at West Kalkaroo, in this western area, we see the weathering just dipping steeply down to 200, 250 metres down the fracture zone. Metallurgists don't like the thought of that because they think it'll be, and mining engineers, because they think it'll be pretty hard to separate the ore, but it's visually it's quite distinctive. You can see a case here where we've drilled through here. We've gone from chalcopyrite here into chalcocite, into native copper, back into chalcocite, back into chalcopyrite, and that's all logged in the mineralogy in the drill core or RC chips. We've been very careful to log the mineralogy so that, and also the degree of weathering. We have partial weathering, partial oxidation, quite a number of things we log. So we're very happy with the accuracy of these boundaries, and it's certainly supported by the assays. So it goes on, it just becomes a mess. But if we go up here to the main zone, for example, let's just take a section. Let's just take a section through here. This is actually crossing the original placer line. It's actually much better behaved because we don't have a deep fracture, or we don't have a fault zone. Basically, you've just got weathering superimposed on the primary sulphide. So down here is all primary sulphides. This is a chalcocite, native copper, and saprolite gold. So if we, for example, took an assay here, looked at the assays, you can see what's going on from the assays. Up here, we're in the saprolite gold zone up here. Well, not actually, we're out of it, the saprolite gold's there, but we've got a bit of a gap, no man's land here. But once you go down below that base of the saprolite gold into the native copper zone, you can see the grades jump up. The gold continues on through. Then we go down to the chalcocite zone, good grades here, still with gold. Then we go down the primary sulphide, the chalcopyrite. And you'll see that in hole after hole. People are a bit sceptical to start with, but when you see it in a couple of hundred holes, you tend to believe the story. So here's I guess another case. If just assays those holes. Okay, you'll see here we're in the yellow ore envelope here. This is saprolite gold, so we've got gold values here. Now you'll say the copper here is fairly high, and it is, but it's not actually cyanide soluble. It's all locked up in limonite, fortunately for us. But this gold here is very fine grained, and it's all cyanide soluble. Then we go down into a bit of a pore. This would be where we first started seeing native copper coming in from our logging. We go through a bit of a pore, not such a good native copper zone here, and that's partly because we're fair way up the sequence. If we come back to here, have a look at this hole, for example. You can see what's going on there pretty clearly. So we come down here, we go through, this is the saprolite gold within this yellow envelope. You see the gold values here starting. No native copper. We go through the boundary of the native copper, the copper values jump up. This is all caused by native copper. Gold still continues on just the same. The only difference here is that there isn't native copper, so the gold is cyanide, can be extracted by cyanide method. Then we go down the chalcocite zone, still nice grades, the gold continues on quite happily. And then we go down the primary sulphides, where it's a bit more patchy in this particular hole, but still economic grade. You can see this is the thing that helps here a lot, and we see this particularly on the nose. Section line here is just here on the nose. See the moly grade. These are moly grades here, so they're pretty spectacular grades of moly. So in many places where the copper is a bit mediocre, toss up whether it be economic or not, fortunately the moly helps us out quite dramatically. So we get quite spectacular moly grades, and you can see it common in the core in fractures and veins through the rock. And down here, of course, we're entirely in the primary sulphides, and it just goes down to the centre of the earth. There again is our limit of our drilling. And again, confined to the prospective sequence between the footwall and the hangingwall, and following the dip. Now, whether anyone's got any questions? Has anyone got any questions? Please feel free to ask if I'm not making sense or I'm going too fast. I hope you're fathoming it all.
Chris, is there any genetic basis for the swap of moly to copper, do you think?
Chris, sorry, can I just interrupt?
Yeah.
Just for the video, could you just repeat the questions if you get questions?
Oh, yes.
So we know what they are.
I'm being asked if there's any genetic relationship, in other words, the origin, what's the relationship of the origin of the molybdenum and the copper. I'm sure they're all related to the same mineralising event, Lindsay, but the moly seems to be where there's a lot more fracturing. It seems to be deeper, and it's quite confined. I'll show you a couple of pictures in a minute of the distribution of the moly. It's quite amazing versus the pyrite. It's always around, it's always associated with the copper, but I think that's about where and I'm sure it's related to generally the same mineralising event, but that's sort of generally where the relationship stops. I'll just draw another section through here to see if just to show you what's going on. So again, here's our gold saprolite. This is the base of the amber clay. So the gold saprolite's getting fairly reasonably shallow here. Native copper zone. Again, it's coloured by copper, so it's always a risk doing these things because you pick a random drill hole and it can prove you a liar. So I've got to be very careful. But you can see that this is within the gold saprolite. This is the gold saprolite ore body here, and you can see the gold values. Some of them get up to quite high values. Sorry, we can't see the values behind there, but you can see why we call this gold saprolite. It's basically gold on its own with very low copper. Bang, we go through this boundary, we start logging native copper. Gold continues on, but you see what the copper's doing. Copper jumps up, and it's all caused by the native copper. Go through the base of the native copper into the chalcocite, and we're still getting pretty good copper grades. Here's another example. Let's have a look at this one. Fortunately, my memory is not good enough to be able to select holes and bias it, so you're pretty safe. Again, this is our gold saprolite. Remember, the grade of the gold saprolite is 0.79 grams, so it's not high grade. We go through that, start to see native copper, and sure enough, up go the assay results. Still getting gold. Go through the native copper, we don't see any more native copper into the chalcocite, and there's the chalcocite rearing its head. And because the mineralisation, we're above the position we're at, there's no room down here for the primary sulphide because this is generally barren. This is sort of footwallish material. So it's only when we get down in here, for example, that below the chalcocite that we're starting to get the primary chalcopyrite. So these grades here, this is reflecting the chalcopyrite grades. And you see there's plenty of gold. There's a direct relationship between chalcopyrite and gold. Absolutely 1-to-1. Very good correlation coefficient. Up here, this is chalcocite again, native copper. And we have some saprolite gold, not much. In fact, it's outside our ore zone. So And again, just to complete the picture, I'll just show you this one here. I find that you get a very good feel for how the ore body ticks when you start just going through all these assay results and just seeing the distribution. So we're below the chalcocite. This is the base of chalcocite. This is the primary sulphide zone here, gold chalcopyrite. And the bulk of because we're down the sulphides here, this is really and this is the width of the ore body. This distance here is about 60 metres. There's not really actually any room to get much secondary mineralisation up here unless it's dispersed laterally. So what else can I say?
What is the nominal depths at, for example, at the shallowest part of your model and at the extents of your mapping?
Yep. Yeah.
To the saprolite gold.
Yep.
The Hangingwall.
Yep. Okay. I can just put up. I'm just being asked what are the depths to the various types of mineralisation, and I can show you that. If I'm smart enough. Yeah, I'm not seeing that. XY, that's why I'm not seeing it. Sure why that is. Labels. Grid. I'll answer your question, Jim. It's a very good question. Here we are. So here's a grid I've just put up. Probably worth a lot more than my trying to describe it. So the surface is about 120 RL. Here, so you can see that the base of the Namba is about 50. That's making the Namba formation here, the air formation, Namba formation, about 70 metres. And then you can see this distance being 50 metres. We're going down another 50, well, we hit the top of the saprolite gold, maybe another 20 metres below the base of the Namba, and then the actual depth that we've drilled to here in this case is 50, 100, 150, 200, intersection, maximum depth of intersection about 200 metres here. So if I put up our, I've still got it here, oh yeah, there's our open pit. So our open pit on this particular section line is going down to roughly 250 metres down here. Now we do have more drilling in here now to justify that, but normally our deepest intersection is around 200 metres, Jim. So to answer your question, which is a very good one, the base of Namba is about 70 metres below the surface. The old water table, where the copper, the native copper was deposited here, is about 120 metres depth. So that you can just about pick where you're going to get the native copper, because it comes in at a certain depth, and it must have been a horizontal water table pretty well, and that's where the native copper is deposited within 10-20 metre fluctuation. The only exception to that is, as I said, at West Kalkaroo, where we've got this great fault, and then it's been disturbed because the weathering has gone down like that. But overall it's around 120 odd metres, pretty well spot on. Right, so I think I can't tell you too much more about it.
Did you use a lot of orientated core to help sort of validate the dome structure and model?
Yeah, pretty well all our diamond cores orientated. This is just interesting thing that's just following on from Lindsay's question earlier. This is just showing the higher copper and higher moly zones. I think this is above 500 ppm moly, if my memory is correct, and I think the copper is above 1%. So you can see that there's an antipathetic relationship in a way between the highest moly and the highest copper. Doesn't mean there's not copper here, there's plenty of copper, but the highest moly tends to be where there's less copper, and the highest copper is where there's less moly. So interestingly, although the moly is in fractures and veins, along this main fault zone which runs through here, we never see moly. So I'm sure Greg Corbett would have an explanation for that. Again, this is cobalt and moly. So here we are, moly above 500 ppm here. It's basically the same as here. But we've also plotted cobalt. There's a lot of cobalt in the ore body actually, associated with the pyrite. So this is really reflecting abundance of pyrite. The cobalt's pretty well all tied up in the pyrite. There's no, I don't think we've ever seen, or there's no known cobalt minerals as such. It's all cobalt tied up in the pyrite lattice. So this is just reflecting more pyrite really, and the pyrite is usually associated with the chalcopyrite. So that's why you also have this sort of antipathetic relationship between the highest grades of cobalt and highest grades of moly, because the cobalt's associated with the pyrite, which is associated with the chalcopyrite. Okay, there is one other thing I can show you. Just slipping back to Vulcan for a minute. The exploration upside actually is an interesting topic. I just have to remove a bit of the clutter here. Get rid of a few of these things and then I can bring up something new. What's happened, because as I showed you before, the mineralisation's open at depth. Naturally, being curious geologists, we always want to see what's at depth. So we embarked on a drilling program fairly recently to actually drill out here depth. So I'll just bring up that. There's only a few drill holes. These are different databases I'm opening, so that's why I've got to, don't necessarily have them all in one database, so we can actually get at them separately. Oops, I think I need that. Okay, so what we did in the last few months was actually to drill down dip and outside the open pit. So these are deep diamond holes. These are the deepest holes we've ever been guilty of drilling. The diamond holes are drilled by Macquarie Drilling of Broken Hill, who did a good job for us, very efficiently. And as we hoped and expected, we showed that the mineralisation continues down dip. So if I actually get my, which I just deleted, I'll put up the footwall, put up the base of the hanging wall, which makes it a bit hard to see, but never mind. You can see on cue, roughly on cue, and remembering this is projected, these surfaces are projected from our drilling up here, but roughly on cue in the prospective sequence, we're finding mineralisation in the prospective sequence. Unfortunately, it's about the same grade as in the main Kalkaroo ore body, run of mine. We would like to have been double the grade, which would have justified bringing the pit down. But as geologists say, we had a great technical success. We proved at least that everything we've been saying about the ore body continuing on at depth and our drilling not limiting it was actually the truth. So now the interesting thing we did find, actually what I'll do is just bring up this. This is a bit of Bob Johnson's doodling here. This is where we project, remembering we're looking at the north plunging nose of a dome, and this is where we would project the prospective sequence to go. Now there is a northern dome up here, and so this comes up, so I can show you that actually. Now remembering this is not quite right because these are not on the same plane. This magnetic should be higher, but if it was you couldn't see it clearly, so the magnetics is deliberately set down below, but you can see what's going on, that the prospective sequence is actually dipping down under here and coming up on the southern end of this northern dome. Anyway, so we drilled out here quite bravely out in the middle of this saddle because we thought we saw an EM anomaly, which might be another fracture like this. And unfortunately the prospective sequence, it was there, but it wasn't brilliantly mineralised. But what did happen, as so often happens in exploration, is that we found a good intersection way up in the Hangingwall P-lights, not in our prospective sequence, which messed up all our good theories. But it's quite significant because if we can find another horizon, well mineralised, good grade horizon up here, it greatly affects the mining economics. So, you know, we're dealing with, this is about 700 metres, so it's a pretty big area that we're dealing with. So it's like, for us, it's like stabbing a needle in a haystack. You'd need a budget of several tens of millions of dollars to drill it out properly. But we were rather hopeful that we might, if we could have found this prospective sequence through here was mineralised, it could have been a billion-ton ore body. It probably is mineralised, but it's probably, at least our indication so far is that it's not economic grade. So anyway, we've had a go at testing some of our ideas, and it's actually correct. The only thing that's beaten us is that the grade is not as good as we would have liked. But as every exploration geologist knows, I mean, if you looked at the original drilling here at Kalkaroo and said, well, you know, it doesn't look to have much potential, you wouldn't have found the rest. And same here. I think there's a huge exploration upside. I think I'll just go back to my PowerPoint. I've just got to, yes. Okay, so that's what I was trying to show before. The ore bodies basically open at depth on each end. This was our saddle area here, which I was trying to show you there. The prospective sequence coming up the North Dome. We drilled out here and actually got quite a nice intersection up in the Hangingwall. And our theory was that maybe the mineralising solutions come up a major fracture here rather than this one, and they fed up dip, much like in an oil dome situation, hydrocarbon sort of geology, which actually I think is very applicable here, because you've got your sealing rock on the top, the pearlites, you've got your porous footwall rocks, and you've got your reactive sandwich meat in the sandwich. Yeah, just showing that it does continue down dip. Yes, this is what I wanted to show you. This is the final slide. So we've talked about the Kalkaroo ore body. We've talked about the saddle area here, immediate, but the regional exploration potential is very good because you still have the prospective sequence coming around all around these domes. We know that. They are cut by major structures where you have this high magnetism. It's indicating iron metasomatism, fine-grained magnetite. And lo and behold, one of the first holes, wildcat holes we drilled, was here where this structure hit the prospective sequence, and we got an ore grade intercept straight up. And because we were didn't believe it, we drilled another hole and got another ore grade. We've never followed that up. Likewise out here, Newcrest, you remember all the Newcrest air core holes? They got a weak anomaly here, right on this structure. There was a gravity low, which is typically, we seem to see where these major fracture zones are because of the deep weathering and loss of density of the rocks. And first hole, we got a hit there. We drilled up here, thinking this was a major fracture zone. Again, a very weak Newcrest base of hole copper anomaly, and we got some quite significant hits there. So just in this Kalkaroo dome, there's huge exploration upside to find more Kalkaroo ore bodies if we had the funding and the time to do it. And if one looks regionally, we're just looking at the Kalkaroo ore bodies here. This is the South Dome, the North Dome, and there are numerous other domes within our tenement area. The Banadgery Dome, where Portia, North Portia are located, Uranella Dome, Mulliungry Dome. And if you happen to hit a hole, put a hole down anywhere near this redox boundary, you're bound to find anomalous copper, gold, lead, zinc. Not economic, unfortunately, every case, but it's definitely a major focus for the mineralisation. There is one other thing I can just briefly show you. I'll get rid of some of this stuff. How am I going for time, Tom? Bit over, righto. Okay. Right, I'll show you one last thing. If I can, smart enough to find it. Okay, so if we just take a regional view now. If we put up the trusted BHI mag gravity, which I'm sure you've all seen. Okay, so if you can do what you can do in any software these days, just sort of shade one or the other, what you find is something very interesting in a regional scale. So I've left the Kalkaroo open pit just there. That's the Kalkaroo open pit, just to give you a perspective. This is a Kalkaroo dome here, highly magnetic Footwall Rocks, similarly Banadgery Dome, Uranella Dome. See the dome beautifully there. The amazing thing is when you put the gravity, what have I done wrong? There we are. When you put the gravity up, superimposed, there's a remarkable coincidence between the gravity and the magnetics. And you can see that this major redox boundary running around here, around these domes, is actually reflected in the gravity as well. There's a marker horizon here which happens to form a subsurface mountain range or low range of hills all the way around the subsurface. Because it's nearer the surface, it forms a gravity high, and it faithfully follows this stratigraphy. You can also see the granites everywhere, just lurking around in the cores of the domes. Here in the case of Banadgery, very close to Kalkaroo, and they're very similar age to the mineralisation. So from a regional perspective, very, very high potential to find Kalkaroo lookalikes when you consider the vastness of the area and the geological settings. Good potential to find more in other domes.